Unit Operation Classroom is a part of an initiative of unitoperation.com. We are now discussing GATE 2024 question 60. A Venturi meter, so this is my Venturi meter, and the water is flowing through it. Throat diameter of D is 2 centimeter, which is this throat diameter right here. Measures the flow rate in a pipe. So this measures the flow rate in a pipe. How does it measure? See any standard textbook how a Venturi meter is used. This is a pretty accurate one and is quite extensively used in the chemical process industry. In a pipe of diameter 6 centimeters. So this is my pipe of diameter 6 centimeter. A U-tube manometer is connected to measure the pressure drop. So this is the upstream end at the throat. U-tube is put in, and here is, let's say, this is my manometric fluid. Could be mercury or anything else. No, let's call it rho m, and let's call this as a water flow. Could be rho w. Okay, and this is manometric fluid density is rho m. Assume the discharge coefficient is independent of the Reynolds number. So in a is a in a so in a Venturi meter equation, this is a very standard equation. So these are the two different forms of Venturi meter. This is the Venturi discharge coefficient, and this is the area A2, and so this is one form. This is another form where beta, of course, is the ratio of the diameters. And again, these are available in any standard textbook. Nothing new here. And we know that this pressure drop between the two, as it flows through it, a pressure drop between the two. And of course, this would be higher pressure and this would be a lower pressure, static pressure. The pressure drop between the two is measured by the manometer, and this delta p. So the delta p between this point and this point, this point and this point, if that's the delta p, and that is given reflected in terms of the height difference in height level of the manometric fluid in the two limbs, and that is given as this one. So delta H is basically this one. Okay, and rho n is the density of this manometric fluid. So if we substitute in this equation here, so if we substitute in this equation, everything else is constant. CD is constant, A2 is constant, rho of the fluid is constant, areas are constant, and delta P only variable is the manometric fluid. So as the water flow rate changes, volumetric flow rate of water changes, so the mass flow rate of water flow rate changes, the corresponding value of the manometric reading, that's the difference between the water level, difference with the manometric fluid level changes. Okay, and as you can see, if we take this equation right here, we can see this is constant, this everything else is constant here except this one. So we can write this was as a constant multiplied by square root of delta H, which is the manometric reading here. So delta H is, of course, is proportional to Q square. So as the volumetric flow rate is doubled, that is, if Q2 is 2 times that of Q1, the height of the manometric fluid, change in the manometric fluid height, which is this one right here, or the manometer reading, is going to be equal to 4. So that is the answer. So basically, this is a very important conclusion because normally these are sent to my DP meter, differential pressure meters in process industries. So that is a very good thing that it must be remembered that the change in the DP readings, of course, are proportional to the square of the volumetric flow rate and of density being constant, the mass flow rate of the fluid flowing to the tube.